Good morning, folks. This is Todd Coburn with your Aerospace Structure series. This lecture is going to continue our study on the lamina or layer, looking at a macromechanical kind of view. What are the overall properties? Last time we learned the stiffness and stress, strain, and stiffness relationships for a lamina in the principal material directions. Today we're going to cover the transformation equations so we understand what those properties are at any other orientation of the lamina. This is not only going to be needed for evaluating the lamina itself, it's also going to be needing to properly accounting for the laminate when we get there. So stay tuned and let's see how it works. So this is a little view of a single layer or lamina. This is a fiber reinforced one. We can see we have directional properties because we have a fiber running in the one direction, and we also have a two direction, a widthwise direction, and a through thickness direction. Recall that we saw when we have a unstrained or no stress applied to one face, and also the material is thin, we were able to reduce our stiffness and compliance matrices, our stress-strain relations, from a 6x6 to a 3x3. And this is what we did last time, like this. These were the inputs for those matrices. We can call the compliance matrix the S matrix and the stiffness matrix the Q matrix. Okay? Now we're going to use S and Q to represent the stiffness of the lamina in the principal directions. If we have that lamina oriented in any other direction, or if for some reason we want to understand how it behaves in another direction, we're going to need a modification of these two matrices. We're going to need the S bar and the Q bar matrix, which has been transformed. And that's what we're going to cover today. So let's say we have a roll. Let's say we're making a composite rocket part. So we're rolling our layers or our each pre-preg layer around a mandrel. Let's say we have two layers, and the outermost layer is at 0 degrees and the innermost layer is at 45 degrees or something, as we kind of see here with this little graphic. Now, in order to evaluate that, we're going to need to evaluate our first layer is oriented. Now, if we have a reference direction, usually we'd run the reference direction for that rocket part longitudinal to the member, as you see the reference shown on the mandrel. And then we will define the orientation of each layer or lamina relative to that. So if that first layer is running in the 0 degree direction, that would be a 0 ply. If the second layer is running at, say, 45 degrees, that would be a 45 degree ply. And we need to remember our nomenclature, which basically is saying from that reference direction, which we're calling X, and we're calling Y perpendicular to the reference direction, what angle does each ply or each lamina have? We're focused on a single lamina here, but we're looking at a couple lamina to just kind of understand how this works. So the X is the body coordinates. We call that body coordinates. You could call it global coordinates. You could call it the loading coordinates. Y is perpendicular to that. And the one direction is the principal material direction of the lamina relative to the reference 0 degree direction. And then the two direction is just perpendicular to that, following the same rotation direction. Our stress transformation equation, if we want to transform stresses from the 1 to the X direction, we would apply this transformation. Basically, you can see we've got whatever happens in the 1, whatever stress is happening in the 1, actually is going to be like a cosine. The component in the x direction is going to be the cosine of that. But we also have the area that that stress applies on, which also needs to be transformed. And if we went through all the trig for that, for each and every element, kind of like we did back toward the end of our Structures 1 class when we looked at the orientation of a loading, taking a cut at some other angle and calculating the normal and shear stresses, we saw that we had to transform the component of the stress, and we also had to transform the area, and we got a cosine squared term and some other terms. And this is following that same procedure, but tracing through what the changes to the one direction stress going from 1 to x, how the stress in the two direction affects that, how that's transformed, and how the shear stress gets transformed. This matrix here does all of that. It transforms the sigma 1, sigma 2, tau 1, 2, and transforms them into the xy and xy directions. So what this means is, if we know what the stresses are in the principal material directions, we can apply this transformation, just pre-multiply those stresses by this matrix, and we will get the stresses in body coordinate directions. On the other hand, if we wanted to calculate, if we had the body coordinate stresses and wanted to calculate material principal stresses, we would take the inverse of this relationship. In fact, let's look at that. We're going to look at that at the next slide. So for stress transformations, we're going to use this transformation matrix to transform our principal direction stresses, to our body coordinate or reference coordinate stresses. You could also call them global coordinates. We can use the exact same transformation to transform our strains in the principal direction to our body coordinate strains. Now notice we're not using the tensor, we're using the tensor strain here, not the engineering strain. So it's the engineering strain over 2, that's the tensor strain, and when we're doing this transformation, that's the value that needs to be here. So whatever the shear strain in the 1, 2 direction is, we divide that by 2, the engineering strain, and plug it into this matrix, and this will give us that transformation. Got it? Okay, now we're going to actually use these, but let's study them a little further. So this is our coordinate system. This was our stress transformation equation. This was our strain transformation equation. Now, in order to calculate the inverse relationship, like we were talking about, calculating the material principal direction stresses and strains from the body coordinate values, we could just take the inverse of this transformation matrix and pre-multiply our body coordinate stresses and strains by that. But that inverse has a very well-defined result, and so instead we could just define the inverse of that like this. So now we're going to call that first transformation matrix, we're actually going to call that the inverse matrix. And we're going to develop what the actual matrix, so we're calling this the inverse transformation matrix. And therefore, we can use that, if that's the inverse transformation matrix shown here, which we see in both of these, then the transformation matrix is just the inverse of that. So these two matrices, T minus 1 and T, we're going to use a lot. One is the transformation matrix, one is the inverse transformation matrix. They're both transformation matrices, but we're going to call the first one T minus 1 and the second one T, and you can actually go from one to the other either by just grabbing that matrix or by computing the matrix, the inverse of the other one. Got it? Now, with that said, we are ready to see what this means in more detail. As we see down here, continuing on, we see now that our body coordinate stresses can be obtained by pre-multiplying our material principal direction stresses by T minus 1, which is the inverse of T. So you can multiply it by T to the minus 1 or by T minus 1. Okay? Our body coordinate strains are calculated the same way. This is the exact same equations that we saw on the prior slide. The only difference is instead of writing out the values of T minus 1, we're just using the variable T minus 1 for that. Now, that means alternately now we can calculate the body direction, body coordinate stresses and strains from the material principal direction stresses and strains from the body coordinate stress and strains by just pre-multiplying the body coordinate stress and strains by T. Okay? So we can go backwards and forwards. So what this means is, as we go forward with our analysis, every time we have a lamina, we're going to need to figure out what is the angle of the lamina and what is the material principal direction variables. E1, E2, G12, Poisson's ratio. We're going to plug those in. We're going to calculate our Q and our S. Actually, or our S. We're going to need to transform those using these equations. So we transform our principal direction stresses to body coordinate and vice versa. Usually what we're going to be doing is getting loads in the body coordinate direction. And from those loads, we're going to need to be calculating the stresses and strains in the material principal directions because that's where our allowables are. Okay? Stand by. So we're going to drill this down further to see how we can do that more precisely. Okay? Right now, what we need to understand is we can use this transformation matrix or its inverse to transform body coordinate to material direction stresses or strains, or the inverse of that relationship. Okay? Now we can, because we've got this tensor strain term here, we can define this Reuter matrix, which basically is the identity matrix except for a 2 in the lower right corner. And we can use this little matrix so that we can do all of these operations with our calculator in matrix fashion. So if that is the Reuter matrix, then we can write our strains. We can transform our tensor strains, E1, E2, and gamma 1, 2 over 2, into E1, E2, and gamma 1, 2, and vice versa. Okay? This is very convenient to make that transformation. Okay. You'll notice here we can transform principal direction strains to principal direction strains. Body coordinate strains to body coordinate strains. What this Reuter matrix does is it leaves everything the same. All the strains are unchanged except for that tensor strain gets changed into a engineering strain and vice versa when we use this Reuter matrix. Okay? This is very powerful so that our calculations can be done in matrix fashion. It seems like a no-brainer, but it is a simple but powerful application of method that will make our approach very doable. Stick with me. All right. So we saw in our last class that this was our relationship of stress to strain. It was the Q matrix, right? Stress to strain in body, the stress versus strain relationship in the material principal direction coordinates was governed by the Q matrix. I already spilled the beans that when we want to go when we have a different angle, we're going to need a Q bar. We're going to need to tweak this Q matrix, and that's what we're going to do now. So we can write that like this, longhand with all the values, or just call it, if we're writing on our paper, it's just the stress matrix is equal to the strain matrix pre-multiplied by this Q. And we're dealing with material principal directions, and since it's a stress versus strain relationship, we're dealing with the engineering strain here. And when we say engineering strain, the only one that is different for that is our shear strain, okay? Everything else is the same. All right. So we saw that our material principal direction stresses can be converted to body coordinate stresses with the use of the inverse T matrix. So we can write our relationship like this. If we just replace in our relationship this material coordinate stresses are equal to Q epsilon times the strain, and we replace the strain with T minus 1 times the stresses, then we can actually, the Q minus the, we're replacing the sigma 1, sigma 2, we're replacing these guys with this guy. And that gives us this. You see that? Okay, and we're going to do this over and over again, so stay with me. Okay. Now, if we focus on the last vector, the strain vector, that was using engineering strain, so we can replace that vector with the tensor strains by switching that out with the R times the strains in tensor notation. Now we're going to focus on that last term, and we see we're going to replace that with T, the transformation matrix, times our strains and body coordinates. Then we're going to focus on that last set of strains, and we're going to place them with the R minus 1 times those strains. Now we're ready to take a look. We're going to take this whole thing, T minus 1 times Q times R times T times R minus 1. And we're going to call all of that Q bar. You'll notice Q is in there, and everything else is transforming it. We're transforming the stress-strain relationship for the angle. We're transforming the tensor strain to engineering strain and back again. All this is done in this little multiplication. And we're going to call all of this, we're going to lump it together, and we're going to call it Q bar, because it's really Q with some tweaks. Okay? Now that we have defined that, remember Q bar is enabling us to deal with non-principal directions for this lamina. All right? So anytime we have a lamina in material where it's aligned with the body coordinates, so the material principal directions are aligned with the body coordinates, we're going to find that Q bar is equal to Q. But anytime it's not aligned or we need to deal with another direction, we're going to need the Q bar. And we're going to have to perform this set of matrix operations. Now this could have been challenging for your parents and their parents if they were in engineering doing all of this by hand. These are all multiplications, so it's not a big deal, but it takes time. You guys have calculators that can do the heavy lifting. So once you put these matrices in your calculator, all you got to do is multiply, multiply, multiply. The key to this is to define your T matrix, and you can actually write a program for the angle that would call those out. Actually, maybe I should make that part of the homework. That will call out that T. Once you have that, and you call it T, and then you can calculate the inverse, call that T1 or something. And now, or you can just do the inverse as you go. Now all you have to do, and then you calculate your Q matrix, and then all you have to do is start pre-multiplying this puppy out. Not too hard. Okay. So this is our Q bar, and now we can write that the stresses are related to strains through the Q bar. Now remember up above, we saw that stresses were related to strains in the material principal directions through the Q, and that remains true. If we have strains in principal material directions, the stresses are related to them by the Q. But if we have strains in body coordinates, we need to pre-multiply by the Q bar to get our stresses in body coordinates. Okay? And the same thing is true. So we can write it, now if we do this, if you actually multiply this out, the entries in the Q-bar matrix can be defined or figured out or written out. And if you actually did this multiplication, this Q-bar multiplication, you would find out our 1, 1 term is given by this first guy. The 1, 2, 2 term is given by the second guy, and so on. This is what you will find if you multiply this out and you look at the entries in this matrix. These are the values. So there's a couple ways to get Q. One is to go, first you calculate Q using what we learned last class. Then you multiply Q in this equation here to get Q bar, and that gives you all the entries of the Q matrix. Alternately, you can take all the entries in the Q matrix and just plug them into this equation to calculate your Q bar. Now, if we were doing all of this by hand and not using the power of a matrix capability calculator, then we would probably find it easiest to calculate each entry in the Q-bar matrix with these equations. We multiply Q11 times cosine of the angle to the fourth plus 2 times Q12 plus 2Q66 times the sine squared cos, and so on. But this is way faster for those of you with engineering calculators with matrix capability to figure out what the entries in the Q are, enter them into your calculator, store them as your Q matrix, and then perform this multiplication for Q bar and store that as the QB matrix. And if you have multiple layers, you're going to want to call those the Q1, the Q2, Q3, or QB1, Q2, B2, and so on. I may try and make a video on this, but you guys can do it. All right. So now we have our Q-bar matrix. We find it by just this transformation right here. On the last slide, I told you how important those transformation equations were. And let me stress how important this transformation equation is. We're going to use this over and over and over and over again as we go backwards and forwards. If you refuse to learn this, you're going to be drowning the whole time. If you've ever been in a pool or been surfing and you get pushed underwater and you kind of almost make it to the top, you almost get your nose above water and then another wave churns you, that's what your studies are going to be like. But if you take the time to master this, you will be buoyant on the water, sitting on your surfboard, paddling through the waves and catching them as desired. So take the time to master entry of T, R, Q, and calculation of Q bar, and understanding how we can go from body coordinates to principal material coordinates and back again, both in the principal material directions and non-principal directions. Okay? You can do it. If you got this far, you can do it. All right. So, we just derived all of this using the stiffness relations. And we can derive them in a similar fashion using the compliance relations. And that's what we're going to do now. So if you want to stick with a stiffness approach, you can ignore the compliance part. Except if you're in a class, it's possible I could ask you to do the compliance too. So if you're in my class, you need to master both concepts. Just focus more on the one you prefer. If you're in industry, choose a method, focus on that. You don't actually need to use both. Okay? So once again, this is relating our material principal direction stresses to strains. And in order to transform that, we can see, look, that's quite an easier transformation. T, the transform of the T matrix times the S matrix times the T matrix. And that means this is our relations. A little bit simpler. Okay? This is all analogous to what we did with the stiffness method. We can calculate the Q bar, we can calculate the S bar. and we can use those to relate stresses to strains. Okay? All right. So this is what we've learned. We've learned that we can go from body coordinate strains to stresses, or from body coordinate stresses to strains using either the Q-bar matrix or the S-bar matrix. Now, this looks like if we want to go from strains to stresses, we need the stiffness approach, and if we want to go from stresses to strains, we need the compliance approach. And while that certainly can be done, you can have one. Let's say you like the stiffness approach. You can use this equation to transform body coordinate strains to stresses, and you can just take the inverse relationship when you calculate the Q bar minus 1 to get the other direction. If you prefer the compliance approach, you can use this relation to transform body coordinate stresses to strains, and you can use the inverse relationship by taking the inverse of the S bar in order to get the other relationship. Either one is fine, but we're going to be doing these backwards and forwards. Got it? Okay. Let's go on to a new idea. This is the main thing we need to master this lecture. But let's take a look at the apparent engineering properties of a lamina. We've been dealing with body coordinate stuff and material coordinate stuff. But it is sometimes convenient to calculate the apparent stiffness matrix in a given direction. Or excuse me, the apparent stiffness in a given direction. So if we were to, I'm not going to derive these for you, I'm just going to give you the equations. If we wanted the apparent, so let's say we have a lamina and it's off at some wacky angle. Let's say this is our lamina and it's at some angle with the principal material direction. Okay? We could take our E1 and our gamma and our everything else, plug it into this equation, and this gives us the approximate stiffness E in that direction. This is a very useful property for doing a lot of simple analysis. We'll deal with some of that later in later studies in this class. If we wanted to do the same thing and calculate the equivalent Y stiffness modulus, we'd use this equation. If we want to get the shear modulus at that angle, this is the equation. And if we want Poisson's relationship for that angle, this is the relation. Now, these equations are in your text, your composite strength handbook. But actually, Jones drills this down further. He derives these for you, as I recall. And he also gives you this little chart. Now, this is curious. What we're doing here is we're looking at normalized properties and how they change as a function of the angle. Okay? So we can see that our stiffness, our E in the x direction is related to our E2 using this. This is a relationship. If we have an angle of 0, if it's oriented, then it's 3 times. And if we have an angle of 90, it's 10%. And it changes like this. Actually, let's go to the next slide where we will study out this idea a little further. Okay? So this is our orientation angle we've been using, and this is the relationship that Jones is showing in his text. Okay? So we're going to actually go through each one. Let's take a look at how the E in the x direction is related to E1. Now, for the graphite epoxy, this is not a general curve that covers everything. This general relationship kind of holds, but there'll be different values for different materials. If we have a graphite epoxy that happens to have a unidirectional one, that happens to have an E1 that's 3 times E2, then you would get this curve. Okay? And if we focus on, we're focused here on this part of the curve here. All right? We're focused on that curve right there. So if we look at that curve, we say, all right, if we have that, if that material, if that lamina is aligned, look, the x and the one direction coincide. That means the EX will be E1, which will happen to be, since our material E1 is 3 times, we'll get a value of 3, and that's what we see here. If, on the other hand, let me erase all this. If, on the other hand, we have our ply oriented at 45 degrees, then we're going to get something much less, and that is this point on the curve at 45 degrees. This is the point. That's now our apparent stiffness in the X. If we're rotated at 90 degrees, let me erase this on the slide. If our lamina is rotated at 90 degrees, we're only going to get about 10% of our stiffness. So a ply that is aligned, for this material, if our ply is aligned with the body coordinates, our EX is going to be about 3 times E2, because it's going to be equivalent to E1. If we're at 90 degrees, it's only 10% of that. This is where John Hartsmith came up with his 10% rule, which we may cover later in this class. And in between, we see we rapidly drop from the 3 times modulus to something much less that very rapidly approaches that 10% value. Just to what Hartsmith postulated was a really fast and dirty rule of thumb is to take any ply that's aligned with the body coordinates and consider its full stiffness, and any ply that's got any other angle, no matter how slight it deviates, and just give those 10% of their properties. It's nice and quick and gives some useful quick approximations. If we look at our shear modulus in our body coordinates and how they relate to G12, we get this curve down here. That's what this curve does. It plots our GXY relative to G12. We see if we have our ply aligned at 0 degrees, we're getting, and at 90 degrees, we're basically getting GXY is G12. But anywhere in between, we're going to get a little more shear stiffness. And the reason is, as you can see in that rightmost plot of that second set of figures, now some of our plies are aligning better with the way this thing's trying to deflect when it's under shear, and that's going to give a slight increase in shear stiffness. And as I said, Jones goes into more detail on that comparison. If we have pure shear acting in the material principal directions, the deformation, we could say that it's matrix dominated. And if we have pure shear acting in a non-principal material direction, we could say that it's fiber dominated, because we're getting a little benefit from that fiber. Okay? If we look at the 45 degree, of the modulus of a ply oriented at 0 versus one oriented at 45 degrees, this kind of shows how that works. Okay? So, and then you also see the Poisson's ratio curve here is also this one here. This is how Poisson's ratio changes for different orientations of the material. Once again, if you want more data from that, I encourage you to go read Jones's text. Get a copy of that. All right. One more topic. Now, this topic is not in your composite strength handbook because it's kind of extra stuff, and I haven't yet put it in there. But this is our relationship. Here's our nomenclature. This is our relationship of stresses to strains in body coordinates. That's all we've been talking about that. Now, these two guys recast these constants. What they were trying to do is figure out a way to understand how material properties change as a function of each value in the matrix. So instead of using the Q-bar matrix, they said, hey, let's calculate some other coefficients, U coefficients, as a function of these Q coefficients. So they define these coefficients here, and once again, we know for an orthotropic lamina, this is true. Okay, great. So far, so good. And we'll see why they did that in just a moment. But before we do, you need to be warned here, because when they did this, they used a different nomenclature than the one we've been using. They used this. And if you look at this carefully, you'll notice this is identical nomenclature except that theta is the negative of the normal theta. Normally, we are going from 1 and going using our angle like that, and they're using the opposite angle. Okay? So this is our nomenclature, and if we look at this chart here, what this shows is, this shows how Q11 changes as a function of theta. We saw that already. But U1 doesn't change. It's invariant that's why they're called invariant properties. No matter what your angle is, this term doesn't change. Of course, the other terms do change. So U1 is the main one that's invariant. Anyway, it's kind of cool. If you really want to be a master of composites, you can study down on this. Once again, I'm going to refer you to Jones's book to understand this in more detail. This is kind of superfluous to what we need because we already have a tool, Q and Q bar. And that tool is calculatable, it's fairly efficient, and it allows us to rapidly move through our analysis. So these invariant properties are superfluous and not really necessary for the average analyst. We could do the same thing for the compliance matrix, and if we did that, we would get a similar set of terms, and these are, we call these V terms, or Todd and Pagano called them V terms. So that is just kind of some extra content. This is not in your text, so people in my classes, students in my classes, will not be expected to use or know these. We will just use the stuff that I have in my text, or the stuff that I add. There are some things that I didn't put in the text that I intend to cover, and I'll give you little supplements for that, because I didn't feel like they were ready for public consumption, or I didn't feel like So this is our invariant properties, not expected to be known by students, but a quick coverage for industry folks that are interested. So that concludes our understanding of transformations. We now understand what the stiffnesses are from last lecture, how to transform those from body coordinates to principal material coordinates and back again. We're going to use these calculations countless times as we move forward in our composite analysis and the rest of the class. So stay tuned.